Of the course, we're going to apply Maxwell's equations to waves in the absence of any conducting materials and any charges. So what that looks like is we're going to use the two that have the curl in them. Curl of H is going to be J, conduction current. I'm just about to cross this out. Sigma E plus dD displacement current density. Okay, so what if we have no metals? It's just a vacuum with zero conductivity. That's what we're talking about when I'm talking about free space. So we have something that we can do if we know a magnetic field of H. We can start applying the curl operator to it and looking at what happens and what's the corresponding D. It's already putting some conditions on what the time derivative of D can be. So there's some connection between the electric field and the magnetic field, dt. We're going to really work towards an equation that links E and H. It's kind of abstract until you start thinking about a plane wave example. Okay, and we can have something to chew on. If we write a expression, and this is going to be a special case, but it's a really useful special case of a magnetic field H that has an amplitude that depends not only on time, but on location. Okay, so when I'm doing H versus time, what I'm doing is I'm putting a little probe at some point, and I'm measuring the H that passes by. It's going up, it's flipping sine, it's going down, and I'm trying to draw an envelope that looks like a sine wave. Oh, missed it. All right. Okay, and H at, say, x equals 0. Another thing we could do is take a snapshot at a single time, t equals 0, and our wave is going to look like this. This is often how we see light waves drawn out. Okay, and then it would be H versus X. How do we write that in math? Plane wave. And I'll tell you why it's called plane wave in a minute. We have an example. H is going to be some amplitude, A, sine, and we've got to have both X and T parts in there. Omega T minus Kx. And now we can look at this expression, and we can see that, yeah, if we set X equal to 0, we can ignore this part. It's just going to be sine omega T. Well, maybe I did a cosine here, so time equals 0. It should have been shifted over a little bit. And if we set T equals 0, then we've got something that looks like a sine with respect to X. And what we have when we have both in there is a traveling wave. And that means you could watch and point on there. And now I'm going to run out of the ability to do this on any kind of whiteboard. If you watch for this node where the magnetic field magnitude is 0, it's going to be moving along. It's going to be keeping this argument 0. Okay, sine of 0 is 0. When Kx minus omega T is 0, I just flipped it around there. Whatever sign it is, the whole thing will come out to be 0. It's node. Okay, H equals 0. And we can watch that thing move along. It's going to move along at a certain speed. Okay, X, we're going to solve this little equation here. X equals omega over KT. It's kind of like location is some multiple of time. That's just a constant velocity. Okay. Node travels at omega over K meters per second. Okay, I'm going to watch that thing truck along. Can't do it on the board. Okay, And why is it called a plane wave? Is this is the value of h everywhere in the, what are the other two components? Y, Z plane. So if this is the x-axis, and this is the magnitude of h, okay, instead of time right here we've got x. Any planes that are perpendicular to this axis, okay, are, and I'm a little flipped around from my usual coordinate system, but we've got y going this way and z going this way. And what this equation is saying is that everywhere in that yz plane, we've got the same value of h. In other words, there's no y's or z's in this thing. So if you set a plane at a constant x value and you look up what this argument's doing, you have to draw magnetic field vectors all over that whole plane, you know, to infinity, that are the same magnitude in the same direction. And we'll look at this little slice over here at a bigger value of x, and it's got a little bit smaller value, and over here I've got 0, and then I start flipping, my magnetic field's doing this everywhere in that plane. So you see what I mean about a plane wave? It's taking this sign argument and putting it everywhere in the other two directions, y and z. And there might be better pictures of it in the book. Okay, and there's certainly good animations online about these waves. Why is this so important? Is this is a really nice expression. Okay, it captures how a radiated wave looks when you're far from the antenna. Sure, it's a spherical wave, but up close, it kind of looks like these wavefronts are planar. You know, there's not much difference over here versus over here. Okay. And so it's very practical, and also we can do the math. We can plug in an expression like this into Ampere's law. Okay, now I'm just keeping these two sides. Plug it in, curl of it, and I mean literally plug that into the curl operator. Instead of h here, we're going to take curl of a sine, oh, and you need a direction on this, omega t minus kx. What did I draw in there? Yeah, I've got it, z direction. Can't take a curl of something that's not a vector. Oops. There we go, z. All right, and good, it matches the picture. So I've always drawn my h along the z direction. So h is in the z direction, but its magnitude depends on x. And in the y direction, it's fairly boring, right? It doesn't point in the y direction, and it doesn't change as you move out in the y direction. Okay. And so if I want to do this, if I want to operate on this thing and take the curl of it, and I'm going to set that equal to epsilon dE dt. My goal here is to find out something about E. At least I'm going to find out its time derivative if I proceed with this. Well, how do I proceed with this? In Cartesian, is curl of h is this, dx dy. Okay, what's my x component of h? It's got to go here. I don't have an x component, and I don't have a y component. I only have a z component. Then I have to put in this whole thing. A sine omega t minus kx. Went out of the thing there. I've got something that I can take x and y and z derivatives of down here. So I'll do that in the next little bit.